Hello viewers and welcome to another episode of Space Science with Python. Today we will reuse the code from last time where we created a dense neural network for the multi-classification purpose to distinguish between the four main groups of the asteroid reflectance spectra. And we will reuse the entire script, but we will replace the dense architecture with a convolutional architecture. So I recommend to have some, let's say, to go a little bit through the theory of convolutional neural networks, so we will not cover it here. So if you have some basic understanding, that's already perfect. And just as a quick reminder, so convolutional neural networks are being used especially for image recognition. So convolutions, or the convolutional layer, they are, let's say, spatial invariant. So for example, if you want to classify a car, it doesn't matter whether the car is in the center of the image, in the top left, the bottom right, or whether you only see a certain part of the car or not, also independent of the colors. So the convolutional network, they apply different number of filters with a certain kernel size. The kernel size is like let's say the viewing field, so the field of view a filter sees, or where the filter is being applied to. And then, for example, in the first layers, you try to, let's speak on the very meta level, you try to identify, generic shapes like circles or squares and so on. And with the deeper the architecture gets, the more, let's say, car or class specific features are then being identified. So you increase also the number of filters. Maybe you can also change the resolution. And then at the end, you are flattening the convolutional layer, creates maybe one or two dense layers, and then you have your final hot encoded classification layer. And today we will do the same, but we don't have images, we have spectra. So they are not two-dimensional information, but one-dimensional information. And we will not we will just create quite quickly some neural network, some architecture, and we will see that the F1 score is not way better than a dense layer because our spectra, they are already spatial invariant. So they all start at 450 nanometers until, I don't know, 800 or so. So today it's more like the purpose to see how to create this convolutional layer. And convolutional layers are also interesting for astronomy. For example, if you have images with galaxies, or later we will also use some spectra that are not 100% invariant. But we can also use, for example, recurrent networks. But we will not cover recurrent networks for now. We will now work with the convolutional layers, because next time I would like to cover an entirely different topic. So we will use convolutional networks. Not 2D, but 1D, and that's what we are going to do today. And of course, I will upload some default model on GitHub, and feel free to change all variables, play around with the filter size, play around with the number of hidden layers to see whether you see an effect on the accuracy or on the F1 score. So the script, as always, is available on GitHub. Just press on the Open and Colab tab and everything should be loaded. Now, there are still some things I would like to mention. So first, let me load some data. And the very first thing is here in the cell number 6. I commented some things out, but it's maybe a little bit interesting for you. Because if you take, for example, convolutional, 2D convolutional architectures, and you apply them to images, the images, they're mostly scaled between 0 and 1. So you have mostly the examples on the internet, they are like, I think, 2-bit and 8-bit encoded, so between 0 and 255. And then mostly the tutorials, they rescale them that we have values between 0 and 1. So you could also theoretically apply the same logic on our spectra data. Our spectra data, they are in a way already scaled at, I think, 550 nanometers, but you can still squeeze it that it's then in a range between 0 and 1. And here I have a code for you, so you can generate this scaling from 0 to 1. So you simply take the all asteroid spectra, You are then subtracting the minimum of each spectrum, and then afterwards you just divide it by the maximum, and then you have to perform some reshaping, doing some magic, but then each entry is a spectrum in a range between 0 and 1. Yeah, feel free to do it, but then be aware that you have to remove also the normalization layer we will add today, which performs some standard scaling. So just for you to be, just to give you some ideas what you can do. Our convolutional network, we will define it in a way that it requires a certain number of inputs. So we have like 49 inputs. And then the second argument is the number of features per timestamp or per wavelength. And this, of course, is 1. We have 1 entry per wavelength. But to enforce this shape, we have to extend our dimensionality, and we use for this numpy expand dimensions asteroids underscore x, and we add an axis 2, so our shape will work. But it's not extend, it's expand, of course. It doesn't have expand. Yeah, good. So if we just add a new cell here, then our shape should look like 1349 and 1 or something like that. Yeah, there it is. Okay, and this will be our input for our convolutional neural network. In the next cell, we have our one-hot encoding of the labels and so on, all the magic we did last time. Stratified, shuffle, split here as well. We will perform some best practices and also some fine-tuning in a future video. Today it's simply about how to build up this convolutional neural network. And of course, our sampling weights needs to be considered as well. And now we are good to go to create our model. So of course, this time I also cleared my runtime. Last time I forgot it, you may remember, and I was a little bit of a mess. But I hope you went through this almost 1 hour video to get a feeling how to code all these things. So if you did not see the prior video number 8 of this project series, then I would recommend it, because there I explain all the weighting, all the data reading and so on. So if you're wondering, wow, what is going on? Where are all the cells coming from? These are the cells from last time, so yeah, feel free to go to video number 8 and take a look at this. Now we create our model, and for our model, as last time, first we will create a normalizing layer, so the layer that applies like this standard scaling as scikit-learn does it. You can also do it with scikit-learn if you want, but the good thing about creating, I cannot talk and write. The good thing about creating a normalization layer is that you can simply later store only the model, and then everything is like done, but you do not need to store a second scaler. So if you do it with scikit-learn, you must really store also the scaling. Otherwise, this information is gone and you do not know how to scale your data properly, because you're applying the scaling based on the data the neural network or the machine learning algorithm is trained on. So in our case, the X train, so X train here, cell number 11 from the splitting. So we have to adapt our X train data to the normalizer, and then we can of course create already our input layer. And for this, we just write input layer equals to keras.input, and then we define the shape. Our shape is like, we call it n inputs, 1, and we have of course to define the number of inputs, and in our case it is from the shape the second entry, or in Python 1, because it starts at 0. Okay, so let's continue. We have our normalizing layer where we simply call the normalizer and then apply our input layer there. So input layer And then we can continue. We can create our first hidden layer. And this hidden layer is now our convolutional layer. So keras.layers conv 1D. So if you do it for images, you have 2D. For even time, for video data, you can even use conv 3D, or if you have larger tensors. But here for our spectra, we use conv 1D. We can then simply also define the number of filters we would like to have. Let's start with some default numbers, 32. Defining an activation functions. Let's use the default ReLU one. And then, of course, also a kernel size. Yeah, let's start with the absolute defaults. Play around with these values, see how they affect the F1 score. But in a future video, we will also see how we can also automate different filters and kernel sizes to really get the best machine learning model from our training without doing wild guesses all the time. One method also, you know it maybe from images, is this max pooling thingy to compress a little bit the information that is being generated by the convolutional layer. So mostly, you create a pool size of 2 or 3. So the information is compressed in by a factor of 2 for conv 1D layers and by a factor of 4 if you have image data. So pool size 2. And then we call here also the hidden layer. Of course, you can give them also some names. I think you can give them names here, even the function, or just change the variable name. I wouldn't change the variable name because it can be quite confusing. Yeah. So if you have like a sequential model as we created here, it's quite okay to have always the same name because then it's being added in the next layer and so on. Just be aware here it's hidden layer. But yeah, don't use too many costume names. I mean, you can do it, feel free, but I wouldn't recommend, otherwise you can get confused. Let's increase the filter size also here. The kernel size can stay at 3. We can also increase it as well. Just also here, there are really nice articles about what are the best practices. Whether this is best practice or not, some of you will write it in the comments, but just see how it goes. I mean, also the information in our spectra is not very varying, right? We don't have a spectrum with sharp peaks or very complex spectra. They are basically like, some continuous functions. So it's quite, you would say, a data scientist would say, they look kind of boring. And of course, a 20-minute video like today cannot really create the best model. Of course, we'll just play around a little bit. So of course, you can achieve higher accuracies with, I think, F1 score of 98 or so. 0.98 is easily achievable, but I think with our very simple structure, we will have maybe like 0.94 or so, which is quite fair. So quite okay for a very quick and dirty project. If you're working in the university, you have a bachelor thesis or so, especially, you have to create a classifier for spectra or so. I mean, take this as a starting point, right? It's just 20 minutes of coding and you have a good starting point, and then it's your task to do the fine tuning and to find a slightly better or adjusted model to for your classification problem. Okay, cool. We are now flattening our layers. So this was the step before we can create our dense layers, as you may remember from the image I just showed in the beginning of the video. And then we can already create our softmax output layer, or even add some dense layer in between. So the output here is 46 dimensions and our output is 4. So let's put something with a factor of 4 less, like 16 or so. Again, creating architectures is trial and error. It is sometimes black magic. It's really not like there's a blueprint for everything. There are some best practices though, like increasing the filter sizes for deeper networks and so on. There's also the best practice to always try to find a regime or a region of overfitting, so that you know that you found some kind of generalized model. So there are some rule of thumbs that apply for this neural network stuff, But don't try to compare yourself with the larger companies or tech companies that create sophisticated speaking models or so, or like GPT-3 or so. They're huge teams with a lot of knowledge, with a lot of expertise, and tons of working hours and huge clusters to perform the training. You cannot really compare yourself with these guys, right? They are creating extremely sophisticated models, and it's not comparable with the small models we create here, but we can create some, we can have some small impact, especially here in space science, or maybe in your thesis or wherever. Good, where am I? I'm now creating the final model where we write the inputs is our input layer. So input layer, output layer is maybe nice wording to get an overview of these things. And then let's see the output layer. And then we have our model. We can return our model. And I already see there is a mistake. Output layer. Yeah, I just didn't name it like this. Okay, cool. And we can create our first model. So create model, and then let's compile it and let's run it over, I don't know, 400 epochs or so with a certain batch size to see whether we see a similar loss behavior as last time. So just some optimizer, and then also the loss, which is the categorical cross entropy. So again, as a reminder, categorical cross entropy is the loss function you need for one hot encoded output class vectors, like we have it here. 4 dimensions, 0 with zeros and ones, so only one. The index of the one encodes the final class. If you have integers encoding your classes, you need the loss function sparse categorical cross entropy. So just be aware of this one. Otherwise, it may lead to some surprising results. Now let's have a look at our model summary. It works nice. We see here, for example, our dimensionality reduces from 49 to 47. If you want to preserve the dimensionality of the input, you just have to add something called padding. So it adds zeros at the beginning and at the end in a way that it preserves the dimensionality. So I think it's called padding equals same. And then and then you see 49, and then you have it. Now you have to be aware a little bit, of course, max pooling. You see here there is some information loss, of course, because we use a pool size of 2 and the input is 49, which means, the half would be like a half a vector or so, which of course sounds broken. And so you have to be aware of all these things. So always take a look at your model summary. But for now, let's keep the padding maybe in the clipboard, and we will work on this later. And now we can conduct our machine learning training, the fitting on the X-train and Y-train data. So let's run this here. I just suppress the output, so verbose is equal 0, and I think this model here in Google Colab takes now like, I don't know, a minute or so. And then afterwards we can also plot our final losses, so this should be displayed just in a moment. So let's wait. Okay, I'm back, guys, and just a small thing. We just had a small typo here in cell number 6, so it was called asteroid underscore x. Now it's under asteroids underscore x, because I just saw here in the model summary that there was a mistake. It was not 49.1, it was 49.49, which was a little bit suspicious. So I just had to go up there, change asteroid underscore x to asteroids underscore x, and then it was finished. So yeah, again, as I always say, Jupyter notebooks or notebooks in general, you have to be really careful and always print out your model and see what you have in there. Otherwise, you can be sometimes a little bit trapped in some wrong assumptions. Now, anyway, we finished our training now, and here is our loss function, or the loss versus the epoch from the training and the validation. So we see the training improves over time. the validation as well, but it reaches somehow somewhere a minimum and then it worsens again. So we have the region of generalization here somewhere around an epoch of 100. And then I already executed the next part, creating an early stopping callback based on the validation loss with a patience of 10. We use the same model again, retrain everything. Here's the same model that is being created. And then afterwards performing some predictions and then also creating the confusion matrix. And here is the final confusion matrix on the different classes called C, S, X, and other. So yeah, this is what I just wanted to show you, and the F1 score is now at 0.96. So quite fair result, I would say. This result, of course, varies a little bit depending on your splitting and, of course, how the weights of the neural networks are being initialized. But I think this is a pretty fair result for a short tutorial. And of course, you can now play around a little bit with the neural networks. So we can add some padding here, like using same padding, and here as well. You can also change the dense layers. So I just mentioned we have 46, but we have 576 because of course it's 9 times 64, not 64. So I had something wrong in my mind. I don't know. But you can also change here a little bit the dense layer to a higher number, or add another dense layer to see if information is being compressed a little bit better than before. So yeah, play around a little bit with the values. We can maybe create a new, we can maybe create just another hidden layer here, or just using the padding. Now let's work maybe with the padding, and also, yeah, we can again also decrease the kernel size to 3, and then rerun everything. Now we have like 0.96 as a benchmark. So I would suggest to restart and run all. So I would always to restart everything just to clear the cache and everything, just to be sure. So let's apply this one and let's perform a new training. So it asks us if we want to rerun everything, and yes, we want to do it. So let's wait for a few seconds, and I'll be back when the training is finished. Okay, I'm back, and here we see now the final results for the padding solution, where we see that some S spectra from the true label S are classified as other. So there's a huge deviation. Our F1 score dropped a little bit. So the padding really didn't improve our classification. But still, it could be improved, or it could still help maybe when we increase a third layer or so, maybe more dense layers. Again, just play around now with the values a little bit. Try maybe to use also some things like AutoKeras or Keras Tuner. So these are some libraries I will show you in the future, because as a human being, let's say, you cannot find the best model from scratch, you know, so there is no perfect solution. You will find you have some kind of solution space, quite huge one, that is depending, or that is being derived from your model architecture. And of course, the possibilities are endless, so you even cannot remotely predict how your solution space looks like. And for this, there are some tools that help you to automate a certain process, automate some hyperparameters of a certain neural network. So yeah, I will just upload, I think, the solution we worked on before. And this is now how the convolutional architecture looks like. So in the future video, we will try to automate our learning a little bit with more neural networks, maybe also creating an ensemble. And for this asteroid spectra topic, we will also work on something called autoencoders. So there are still some videos left, I think 4 or 5 videos left for this project. And then afterwards, we will step back a little bit. We will work a little bit on near Earth objects. We will not apply machine learning for now, but don't worry, a lot of machine learning is still to come. And of course, this project is not finished yet. So as always, I hope you enjoyed today's video and also you learned a little bit how to build up a simple convolutional neural network, and again, took a look at the metrics and so on. And if you would like to apply this on your problem, feel free, or even you have your current thesis is about asteroid spectra, then yeah, this is something like a small solution for you. Okay, cool. Thank you very much, guys, for listening. And I would say we see each other next week. Talk to you later.